One thing you guys may have been thinking about when we talked about going from a more dense to a less dense medium in the last set of notes was what happens when my angle gets so big because I'm bending away from the normal that I bend away more than 90 degrees. Well, you get what's called total internal reflection. So like we showed in the diagram in the last set of notes, you get some reflection and you get some refraction. But as you get closer and closer to a specific angle, when you're going from a more dense to a less dense medium, is you can get entirely reflection. You get less and less refraction, more and more reflection until you're at 100% reflection. Let's see why that is. So again, this only happens when we go from something that is more optically dense, higher index of refraction, to something that is less optically dense. So as you increase that angle of incidence, the angle the light's coming in at, eventually you're going to get your second angle bending all the way to 90 degrees because remember, you're bending away from the normal. You're speeding up when you get to that media barrier. This angle where you get 90 degrees as your refracted angle is called your critical angle. So when your incident angle is equal to your critical angle, then your refracted angle becomes 90. That's a lot of words. Let's look at a diagram in just a second. But if you try to go anywhere beyond that, all you're going to get is reflection. So beyond that angle, you'll always have total internal reflection. That's where we get all of the light is being reflected inside the substance that it came out of. So let's try this one out here. I want you to determine the critical angle for water, which has an index of refraction of 1.333 to air. If you guys have ever been in a pool before, you've probably looked up and directly above you, you're able to see the sky. But as you try and look further away, all it looks like is the bottom of the pool. So I want you to go ahead, use Snell's law to try and figure out what our critical angle is as we go from water to air so that we can get total internal reflection. Okay, we'll see if you got it. So here's Snell's law like normal. N1 sine theta 1 equals N2 sine theta 2. But specifically, we're looking for when sine theta 2 is equal to 90 degrees. Well, we know sine of 90 is 1. That's when theta 1 is our critical angle. So I'll go ahead and put critical here. So sine theta of the critical. I just multiply by 1, so now this is just N2. Divide by N1. Take the arc sine of that side. So now I have N2 over N1, arc sine of that quantity. So the arc sine of 1 over 1.333, and I get 49 degrees. So that's why when you look up, if you look a little bit below a 45-degree angle away from you, the pool just looks like the reflection, the bottom of the pool. So here's our diagrams here. When sine theta, when our theta, the angle that we're incident to the surface, the barrier change, is less than our critical angle, we're still getting refraction. But eventually, as we continue to increase the size of this one over here is going to bend more and more towards the normal until eventually we get a ray that is exactly parallel with the normal. Now, anything beyond that, we're getting total internal reflection, which is why when we continue to increase our angle, now it's just light reflecting back in there. Now, I want you to leave a little space in your notes. We'll do a couple demos with total internal reflection, and we'll also have a lab with it. So go ahead and leave a little space in your notes, but that's going to do it for all of our notes on waves and light.